We're going to continue with big idea 2, and we are going to get into how to draw compounds. You did quite a bit of this last year in honors in terms of single, double, triple bonds, but you didn't learn about expanded octets, so we're going to explore that as well, and the next time we'll get into the shapes as well as the polarity of molecules. A lot of what we do today is review. But one thing I cannot emphasize enough to you is you must practice. You must practice drawing these compounds. Just because you watch me draw one or you've drawn 2 in class, it's not enough for mastery. Be very careful there. There are some key tricks we're going to learn today to make sure you draw compounds correctly, because your drawing will then lead into shape determination, polarity determination, etc. And you'll be exploring a lot of that in the lab probably first thing next week. Last time we left off going over some basic terminology. So let's just take a minute to review that. For example, this is actually something I did in honors. This is the only time honors in AP are actually talking about similar concepts. Remember last time, we can focus on this middle column here. The molecular formula tells you which atoms comprise the compound and how many of each you have. The skeletal structure gives you the arrangement of the atoms. The structural formula shows you how the atoms are linked together, as well as lone pairs of electrons on, in this case, a terminal atom. Terminal atoms are connected to only one other atom. Keep in mind that hydrogen must be a terminal atom. Must. Halogens are usually terminal, but this year you'll see that they can be central as well. Central atoms are connected to at least 2 atoms. So central versus terminal, we mentioned last time, lone pairs. And this is all from honors this year, so you would have seen it last year, and hopefully your level of understanding there is high. What we're going to do now is talk about the steps we take to draw structural formulas.
Can you say that the central atom needs to be connected to at least 2 other atoms?
2 atoms, but they can be 2 of the same, like C to C.
But then, so that's how like a halogen, and then have the halogen become a central atom.
That you're going to see this year. So you never saw it before, but you'll see it this year. Because typically, last year you always saw halogens were terminal with 1 single bond and 3 lone pairs. This year you'll see a difference. But that we'll get into.
What page are we on in the note?
We are going to pick up
5, I think.
Page 5.
right here. We're going to go through the method for writing, and it looks like I'm going from 4 to 5. Yep. Certain steps you want to follow. The first step always, and critically important this year, is to get the total number of valence electrons for your compound or polyatomic ion. For example, when you're getting the total number of valence electrons, let's say, for example, you had methane, CH4, carbons in group 14, it has 4 valence electrons. You have 4 hydrogen, each with 1 valence electron. Total number of valence electrons in that compound would be 8. Let's say, for example, you had ammonia, NH3. Nitrogen has 5 valence electrons. Hydrogen, you have 3 of them, each with 1. Total of 8. Let's say that you had ethyl chloride, 2 carbon, each with 4, 5 hydrogen each with 1 chlorine in group 17 with 7, and that's going to be 12 and 8 is 20. Getting the total number of valence electrons will be critically important this year. Don't forget. If you have a polyatomic ion, such as a sulfate ion, you'll go about it similarly with one difference. Sulfur has 6 valence electrons, group 16, 4 oxygen each with 6. You have a 2 minus charge. So that ion formed through the gaining of 2 electrons. So you will add 2 more. And you have 32 valence electrons here. Try this one, phosphite ion. And I usually put the valence number in parentheses, so maybe the extra electrons you don't want to put in parentheses, maybe that would be the distinction you're looking for. If you need a pink periodic table, they're on my desk. By all means, help yourselves. You should have a purple one in your notes.
Why is it 6?
Why is what 6?
Where do you get the
4
6
times
from?
6.
Why isn't it 4 times? Oh, because oxygen has 6 valence.
Yeah, oxygen and sulfur in group 16 with 6 valence.
Oh, I just got confused.
That's all right. We can do this one together. Phosphorus would have how many? 5, group 15. 3 O's each with, and we're going to add 3. And again, I was just trying to make this distinction clear here. So we have 18 and 8 is 26. And you'll often have to do this without a calculator. All of you are extremely strong in math. You're in pre-calc, AP Calc, and then some. Should be gold in there. This one's slightly different, but nothing that's going to blow you out of the water. Here's an ammonium ion. Nitrogen has 5 valence electrons, 4 H's each with 1, and now you will subtract 1 exactly. So you have 9 minus 1 is 8. Easy peasy, right? First step in figuring out how to draw a compound is to get the total number of valence electrons. Critically important. The second step is to write a skeletal structure. And if you have to guess, choose the structure that's the most symmetrical. We'll illustrate that concept in a few minutes, as we'll illustrate a bunch of concepts. The next step says use I added mental right here because you already know as much as you want this chart, you're not going to get it, to determine how many bonds each atom typically forms. Remember, for period 2, it's typically 8 minus the number of valence electrons to figure out the number of bonds. Hydrogen only forms 1 bond. Hydrogen will always, 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 always be a terminal atom. Please don't use hydrogen as a linker or a central atom. That is a recipe for disaster. Halogens typically form 1 single bond, often terminal atoms. That's what you saw last year. This year you'll see that halogens can be central atoms. Little bit tricky there. We'll give you some examples. Carbon typically forms 4 bonds, singles, doubles, or triples. There are a few instances that I will show you now because sometimes they come up where carbon forms 3 bonds and has a lone pair. Unless you have the 2 examples I'm going to show you, please don't leave lone pairs on carbon. One example where carbon has 3 bonds is carbon monoxide. This is a little unusual. Carbon's going to have 3 bonds, and you'll have a lone pair on the carbon and the oxygen. So that's one instance where carbon forms 3 bonds. Otherwise, it typically forms 4. Another instance is a cyanide ion. We're going to go over how to draw structural formulas for ions. When you have an ion, immediately use brackets and put the charge on the outside. No brackets, no charge, no credit. Disappointment. C, triple bond to N, and this is another instance where carbon has a lone pair of electrons. Otherwise, I can't think of other instances where it does.
Why would carbon have a lone pair? It only has four. It has 4 electrons, and if you're doing a triple bond, it's already sharing 3 of them. Where did that react?
What you're seeing here, for example, in each of these instances, you have an octet of electrons around each atom. Each stick is 2, 2, 4, 6, 8 octet of electrons around carbon, 2, 4, 6, 8 octet of electrons around oxygen, 2, 4, 6, 8 octet, 2, 4, 6, 8. But I think maybe you're asking where they came from.
Yeah, because carbon has 4 valence electrons, and then and it's already sharing 3 of them with the triple bond. So where did it get the 5th one to get the lone pair?
Okay, so when you're drawing it, if you go back to the way you initially learned, you have 1, 2, 3, 4 for carbon. 1, 2, 3, 4, 5, 6 for oxygen, correct? Lone electrons make friends and they move between atoms where they can accommodate a shared pair. So this guy and this guy hook up and move between the C and O. And this is an instance, and this is kind of funky now. These 2 electrons will pair together because a lone pair is more stable than a single electron. So they'll pair right there, and then this electron pair actually moves between here for the other bond. Or you might argue this electron and this electron hook up, and then you want to satisfy each octet, and so this electron may yank this one over. So I'm actually not sure exactly how you derive that. I'm not sure it is known, and I don't see how you can label atoms radioactively, but in regard to their electrons, I don't think that would hold true. So I'm not sure. I could try and find out. It's an interesting question, but more than you need to know. Alrighty, so these are the 2 instances where carbon forms a triple bond and there's a lone pair on the carbon. You don't see very much of it, but carbon monoxide sometimes does come up. Continuing on then, nitrogen typically forms 3 bonds, 1 lone pair, sometimes 4 bonds. Oxygen typically forms 2 bonds, 2 lone pairs, but sometimes it'll form a single bond and 3 lone pairs, or a triple bond and 1 lone pair like you just saw. Sulfur and oxygen are in the same group, so they do have similar characteristics. However, sulfur is in period 3. It can expand its octet, and you're going to see that it can form 3, 4, 5, and 6 bonds. Phosphorus also is in period 3. It will be similar to nitrogen in some regards, but phosphorus too can expand its octet and form 4, 5, or 6 bonds. Boron and beryllium are a little unusual. They don't have complete octets. Be very careful with those. Boron forms 3 bonds, no lone pairs. Beryllium, 2 bonds, no lone pairs. And we'll talk a little bit, especially about boron, in a little while with our incomplete octets. You're going to see a lot of this sometimes this year where you wouldn't have seen much of it at all in honors because you're going to learn about expanded octets in a bit. All right, so we're going to figure out valence electrons. We're going to write the skeletal structure. We'll figure out how to place those atoms based on the atoms forming the most bonds. We're going to place pairs of electrons as lone electrons around terminal atoms to make sure terminal atoms have an octet. Hydrogen, of course, only has a duet. You're going to assign any remaining electrons as lone pairs around the central atom. If necessary, you'll move those lone electrons to form multiple bonds. Remember from last year, C, N, and O can form singles or doubles. C and N can form single, doubles, triples. We'll be cognizant of that. And we're going to go through and draw all of these. I would think all of you can draw these off the bat. A lot of you can draw that one, and we'll get into the new pieces of the puzzle today. So I would think all of you could draw this with ease before I even go through it. A lot of you could draw the adorable little Ku group. And then these will be more new where you've got a halogen as a central atom. So let's take a look. We're going to walk through all the steps. We're not going to dot ourselves to death. We're really going to take some shortcuts here. Most of you would have taken these shortcuts in honors anyway. Best and brightest moved up. And I'm sure your drawing of compounds was very solid. The first example is ethyl chloride, and we had done this one previously. We've got 2 times 4 plus 5 times 1 plus 7 more, and we've got 20 valence electrons. I blew through that quickly because we had already done it. Next up is the skeletal structure. Very often the way it's written is how you draw it. You know H has to be terminal, so don't put that down yet. You've got 2 C's and a Cl, and it looks like we have 5 H's on carbons. We've got 1, 2, 3, 4, 5 positions. And this should look familiar, yes? Okay, good. Next thing I'm going to do, carbon typically forms 4 bonds. 1, 2, 3, 4. 1, 2, 3, 4. And here's the importance of the count. Some of you are going to be like, ooh, that's it. But if you went 2, 4, 6, 8, 10, 12, 14, you would note right away that you're missing what? You're missing 6 electrons or 3 lone pairs on the halogen. Easy peasy, right? All right. Also equally as easy will be the next one. Nitrogen trifluoride. Get your count. Nitrogen with 5, each fluorine with 1 for a total of 8. What atom is likely to be central? Nitrogen. Fluorine will never be central.
Is it because it's electronegative?
So electronegative. The most electronegative.
Those are the IMFs, right?
No. IMFs are intermolecular forces. So if you had nitrogen trifluoride and you have a whole bunch of them, that's how those interact with each other. So these, that's an important distinction to make. Hang on. This, of course, is a covalent bond. A covalent bond is an intramolecular force within the molecule.
So IMF, like the abbreviation, is inter.
Inter.
Doesn't fluorine have 7 valence electrons?
Yes. 21 and 5 would be 26. I think I switched to oxidation number. Guys, I made a boo-boo. Let's fix.
Is there a case in which fluorine would ever be a central atom?
No. That's why you don't have an oxyacid with fluorine. Guys, I rushed here. I was sloppy. Nitrogen has 5. There are 3 fluorine, each with 7 valence electrons. Its charge would be 1 minus. So you have 26. Nitrogen will, of course, be the central atom, because fluorine can't be. And nitrogen's less electronegative. Your lower electronegativity atoms are typically central, with a few exceptions. Hydrogen, no. Connect. Complete octets on terminal atoms. When you count, do something systematic. I typically look at dots. I know I have 6 dots around each fluorine. 6 times 3 is 18. 20, 22, 24. What's missing? The lone pair of electrons on nitrogen to complete its octet.
So is this the only orientation of the fluorine that would work? Because then if we tried to write it a different way, it wouldn't work.
Try hydrazine. Did you get what I got?
Is it okay if you put the hydrogen on top of your nitrogen?
Doesn't matter. Actually, when you draw it properly, it's a trigonal pyramidal, so the bond angle is 107. We'll get into that next time. Although you may remember trigonal pyramidal from last year vaguely.
There's like trigonal pyramidal and there's like trigonal plane.
Last year you learned about trigonal pyramidal, trigonal planar, tetrahedral, linear, and bent. And this year you're going to learn about seesaw and square planar and square pyramidal and trigonal bipyramidal and a whole bunch of other fun little shapes.
Okay.
It's actually really fun. It's like a puzzle.
The kids usually love drawing. But like everything else in here, you've got to practice. If you don't practice, you're going to be messy.
Is there a textbook practice?
Tons of it. Highly recommend it tonight for mastery for next time. Never know when you get a pop little quiz.
Oh
All right, phosgene. Phosgene.
How'd you say it?
What atom? All right, let's get a count. 4, 6, 2 times 7. 14 and 10 is? All right. Central atom? Think symmetrical. What are you thinking?
Double bond and a single bond. 2 single bonds.
Complete octets of terminals?
Does it matter if you put the oxygen underneath this?
Nope. It actually has a trigonal planar structure, so if I were drawing this properly, it would look like that.
Are we going to need to like be able to draw
No,
in like the correct shape?
no.
Sweet.
Just as long as we have like the right spot, like bonds.
Yep.
Why don't we teach naming?
What?
Why don't we teach naming?
Well, this is funky naming,
Yeah, like Oregon.
but this is different. This is not organic naming. If your halogen is a guys, this is a good question. If your halogen is a terminal atom, I think in almost every instance, can't think of one where it isn't. If your halogen is a terminal atom, it's going to have one single bond and 3 lone pairs. Try this one.
Cosine. Hey, you can make sine too.
Not so much.
You can't make yoga.
Is that what you got? So you're like, this is a waste of my time, Dr. Kalish. This is just too easy. Well, let's bring it. This one's easy too. You do. And you're going to see, some of you are like, I don't need this valence count. What's her problem? You're going to see you're going to need it. No. Typically, they'd go here and here, but I'm trying not to do that to keep it simple for you. Alrighty, I want to go into the coup group. Some of you draw the coup group to death last year, and you will be very grateful for that. What you're looking at here, you've got 3 C's, and the coup group is always C double bonded to O, single bond O, H, like that.
Groups are high priority.
They're high what?
Priority.
What do you mean priority?
Like you name it first, right? Like don't,
No.
aren't they highest priority?
Oh, I know what you mean in terms of numbering.
Yeah.
Their number isn't usually specified, but we're getting off track. I'll answer that separately because it's just going to be confusing, but it's a good question. This is a carboxyl group. You see it with carboxylic acid. You see it with amino acids. In any event, you've got 3 H's to place. So what are you thinking? 1 on each carbon's probably not going to work.
All 3 hydrogens.
Yeah.
What do you want to do?
All 3 hydrogens on a Cl with the left.
You want to put it here?
Yeah.
Yeah, that'll work. But there's another possibility, which some of you may have seen.
Yeah, triple bond.
So that's one possibility. Another one, I'm just going to coup it that way. Another one would be this.
And why did that one work?
Why does this work? Does carbon have 4 bonds in every instance?
What is the name for that when they like the different
Isomers.
Yeah, and that's exactly where I was going. These are isomers. Isomers have the same molecular formula, but different structural formulas. You don't just take a mirror image. You don't just take it and flip it on its back or flip it on its tummy. You have to truly move something. Where you might have had single, triple, now you have double, double. I'll give you a better example of isomers that'll be easy to see and it'll feed into not the lab we do next week, but a lab after break. Another example that you see for isomers, and Chase, this one's just for you, for naming, is you could have the molecular formula C3H7 OH. You could have 1 propanol, or you could have 2 propanol, which is isopropanol.
Yeah.
Isopropanol is rubbing alcohol. In this case, you have C, 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 and the OH comes off an end carbon.
Should we copy this?
Your call. You're going to see isopropanol in a lab. You may want to.
Do we need to know the chemical formula for it?
No. And 2-propanol is when the OH, this is a hydroxyl group for those of you who have taken AP Bio or are going in that direction next year. That's 2-propanol. These are isomers as well. You've moved the functional group. Isomers have the same molecular formula, but different structural formulas. You'll be using different percents of isopropanol in the lab when we do liquid chromatography for intermolecular forces.
Can I re-ask my question? Like, so if you had like a branched alkane on the first carbon, you would name the hydroxyl group first, right?
Yes, but with carboxyl, it doesn't always work in that regard. All right, here's a new piece, and this is going to be the chlorate ion, new at multiple levels here. Again, get your electron count, 7 valence electrons for the halogen, 6 for the 3 O's, and you're going to add how many? 1, because of the 1 minus charge. 18 and 8 is 26 valence electrons. When you go to draw this, immediately put a bracket in and the charge on the outside. Can't tell you how many brilliant kids I've had who never could remember to put these ions in the brackets and indicate their charge. Now we said you want to think symmetrical, and this is an instance where the halogen will be the central atom. Keep it simple. 1, 2, 3. Complete the octet on each oxygen.
Then why did the other oxygen? Never mind. I remember.
Count your electrons. You have 6 times 3 is 18, 20, 22, 24. Complete the octet on the chlorine, and you have 1 possible Lewis structure for chlorate ion. There are some other ones that we will explore in a little bit. The other ion there is cyanide ion. That's one we already did, so we won't redo it. What helps you determine which structure is the most plausible is formal charge. Formal charge is defined as the difference between the number of valence electrons in a free uncombined atom. That's right off the periodic table. So if it's oxygen in group 16, it'd have 6, versus the number of electrons assigned to that atom when it's bonded. Now this is a hypothetical charge because we know atoms don't carry charges. To calculate formal charge, you'll do number of valence electrons in an uncombined atom minus the number of valence electrons assigned to the bound atom, and I'll show you how to do that. Typically, the best plausible structure is the one with no formal charges. We'll take a look. If formal charges are required, you want them to be as small as possible, and in most cases, the more electronegative atom will have the negative formal charge. There are a few exceptions to this. I'll show you that with carbon monoxide and cyanide ion. Adjacent atoms in a structure should not carry formal charges of the same sign, and the total formal charge should be equal to 0 if you have a compound or the charge on a polyatomic ion. We're going to look at these structures that we've drawn in our notes, and we're going to figure out the formal charge for each atom in the compound. So we're going to backtrack now, which is why I tried to keep this very neat. I hope you did the same. We want to figure out the formal charge on each atom in the compound here. And the way we do formal charge is number of valence electrons in a free atom minus the number of electrons attached. I'll show you how to do that piece. Carbon. We want to figure out formal charge. Carbon by its lonesome, 4 valence electrons, minus, in a bonded situation, only what's directly attached to the atom. 1, 2, 3, 4. 4 minus 4 is 0. The chlorines are both the same here. Chlorine, group 17, 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. 7 minus 7 is 0. Oxygen, by its lonesome, how many valence electrons? No, 6 is correct, group 16. 1, 2, 3, 4, 5, 6. This structure is beautiful. No formal charges on any atom. Looking at this one.
Is this how it's gonna work? Where if it's not an ion, all the charges are gonna be 0, or the formal charges?
Nope, nope, nope. You'll see. Looking here, what's the formal charge on this carbon? 0. 4 minus 4 is 0. This sulfur? 6 minus 6 is?
0.
Oxygen? 0. Let's look at the chlorate ion that we drew. These two oxygen, free element would have how many valence electrons? 6 minus,
6.
nope, now watch. 1, 2, 3, 4, 5, 6, 7. So the formal charge on each of these O's is -1.
Why isn't it 8?
Because it only shares 1 electron in each bond. That electron comes from the chlorine.
Let's look at the chlorine. By itself, how many valence electrons? 1, 2, 3, 4, 5. Formal charge of +2. Not the greatest structure, but 2 plus 3 minus 1 is -1, so that looks good. The more electronegative atom, oxygen, has the negative formal charge, so that's a good sign as well. You already have cyanide ion in your notes. It's easier for me to just redraw it. then to find it. Might be easier for you to redraw it too. This one's a little unusual. Formal charge on the carbon here is -1 is correct. 4 minus 5 is -1. Nitrogen,
0.
5 minus 5 is 0. Now this one's a little unusual because this is not more electronegative than nitrogen. You know, as you go across the period, the electronegativity increases. But nonetheless, this is the best structure. And you see it a little bit unusually for carbon monoxide as well. Carbon here is going to be -1, and the oxygen will be 1. So here's your question, Andrew. And you can see that they don't always have formal charges of 0 in compounds, but the sum will be. This is also unusual because the more electronegative atom is oxygen, yet it doesn't have the negative formal charge. Typically it would. All right? In 2005, they had a cutesy little question right here. It says 2 Lewis structures can be drawn for OPF3 as shown. They provide you with structure 1 and structure 2. Sigma and pi you'll know how to do next time. It says which one of the 2 structures best represents a molecule of OPF3. Justify your answer in terms of formal charge. What do you think? On the first one, the formal charge on each fluorine atom is 0. Phosphorus is 0. Oxygen is
2.
I get 0. 6 minus 6. Right? So no formal charge on any atom here. In contrast, what's the formal charge on the phosphorus?
1.
1 is correct. 5 minus 4 is 1. And on the oxygen is?
1.
6 minus 7 is? -1. So the best structure is the first because all the formal charges on the atoms is 0, whereas in the second, the phosphorus has a +1 and the oxygen has a -1. Okay?
That's all there's the rest.
Yeah.
Wait, why does, like on the first one, phosphorus has 5?
Right, because as a free element, it has 5 valence electrons in group 15. And now look at the attach. 1, 2, 3, 4, 5. 5 minus 5 is 0. And again, I can't emphasize enough the importance of practice. Practice, practice, practice. You should spend at least 2 hours before your next class period drawing these compounds out. It is the only way you're going to be very strong with it. Let's take a look at resonance, and then we'll take a short break. Resonance is very tricky. It's something that is listed on or in the honors curriculum, but it is such a tricky concept. I don't even teach it anymore at the honors level because I know how much AP struggles with it. With resonance, you have delocalized bonding. What you're looking at here is if you have a molecule or an ion that can be represented by 2 or more plausible Lewis structures that differ only in their electron distribution, we say that the true structure is actually a composite or a blending, a hybrid of those structures. You're going to use resonance when more than one valid Lewis structure can be drawn, and you'll see that the resulting structure is actually an average of the resonance structures. Let me illustrate with a few examples.
When it says the valid Lewis structure, that just means anything that when you add all the formal charges together equals the complete charge. like in the last one that we had, both equaled 0, but the other one was better.
Right. But in this instance, in the case of resonance, I think I'm 99% sure, we'll double check this, that with these resonance structures, their formal charges are going to be consistently as good. So one will not be better than the other. You didn't see resonance previously.
When it says differ only in the distribution of electrons, does that mean like moving around, like doing isomers?
No, not isomers. That's what I'm going to show you.
Okay.
Hang on. It's a good question, and we'll make the distinction clear, but it's an excellent question. All right, so what we're looking at then, for example, ozone, common example that they love. The other one is sulfur dioxide. We'll look at both. Ozone has 18 valence electrons. This is one of the few instances where you link O's together. You see it also in peroxides. So we have 6, 8, 10, 12, 14, 16, 18. That's one possibility. Now what's to say that it wasn't this structure? And this is going to bother you a little bit because it looks like a mirror image, but we've changed electron distribution. These two structures designated by this arrow between them are resonant structures. They differ only in the distribution of electrons. If you measure the length of the O to O bond, you don't actually find that one's a single and one's a double. Instead, you actually find that the bond length between the O's is the same, and its length is going to be equivalent to 1.5 bonds. And so what you have is really a blending of the two structures. These are resonant structures. You can figure it's 1.5 because you have a single and a double. You have 3 bonds shared between a central atom and 2 oxygen atoms. And I'll show you how to calculate that number in a little bit.
3/2.
You can calculate it as 1, 2, 3 bonds divided by the number of identical atoms attached. Be careful, because I'll show you what happened to the kids last year, or 2 years ago rather. They came in and there was a mistake on the AP exam, and I said, I seriously doubt it. And they were wrong. There was no mistake. It was all their misconception. But we're going to clarify that for you this year so you don't make that kind of error. Here's ozone. Similarly, the other great example is sulfur dioxide. Also with 18 valence electrons, it's going to look grossly similar. And here too, between the S and the O, you actually have 1.5 bonds. And they love these two questions, or at least they used to. So you really have 1.5 bonds between S and O.
So then when you draw the one with the dotted line, you don't put the lone pairs because it's...
I just didn't. I was lazy. I'm just you wouldn't actually draw it this way. It just shows 1.5.
Oh, so that's not like the answer.
No.
Wait,
Where's what?
where does 1.5 come from?
one single and two double shared between one central atom and two O's. You can calculate it as 1,2,3,6 divided by the two atoms attached. 3 over 2 is 1.5. I'll show you a couple examples there.
Do you have to show both structures?
If they ask for it, let me show you the question and you'll see why you'll need it.
Okay.
All right. In 2016, so this is a recent AP exam question, redesign. I want to point out a few things to you. In this question, and this is why it's difficult to really bite into these questions early on, you're given an equation, you're given some information, and the first question says, identify the reaction represented above as an acid-base, precip, or redox reaction. And you should be able to do that already because we talked about reaction types. The next question says, identify the limiting reagent. You should be able to do that because you did it with ease last year. Then it indicates something about kinetics, which we've also covered already. Then they get into thermo, which most of you couldn't answer at this point, although some of you would remember it from honors. Here's the piece that deals with what we're talking about now. And so on these questions, they're not just assessing a single concept, and that's what makes it so challenging. That's why the exam is curved so much. That's why it's okay to get a 70 on your quiz and have it be an A. The only problem is your quizzes are covering just a few concepts. Wait till we've covered a whole lot of concepts, which we actually have already, and we mix them all together in the form of a semester exam. You must have mastery of the concepts we've already talked about. In regard to this concept, we're going to read very carefully, and you can tell me why so many of my kids told me after the 48-hour waiting period that they thought they should draw carbon with 5 bonds. I told them, didn't think that was a great idea. For some of you, this is your first AP exam, and you take it and you wait 48 hours to talk about part 2.
Why?
Because that's the rule. All right, on E, it says the bicarbonate ion HCO3 has 3. Listen, listen, listen. This is why you're struggling on your quizzes. You don't read the question, which is why your answers are wrong because they don't address the question asked. The bicarbonate ion has 3 carbon to oxygen bonds. 2 of them have the same length, and the third is longer than the other 2. The hydrogen atom is bonded to one of the O's. In the box below, draw a Lewis electron dot diagram or diagrams for the bicarbonate ion that is or are consistent with the information provided. Let's take a look at what they told us. Now, if my students at that point in their chemistry career had just been given this polyatomic ion and been asked to draw it, I think they would have done it correctly. They didn't want to read all the gobbledygook, and so they made a mess.
They literally tell you how to go.
Well, be careful. It says 3 C to O bonds. It tells you that 2 have the same length and 1 is longer. Hang on. It tells you that the O is hooked to an H.
It says that one of it, right?
Yes. Well, you only have one H, right? What do you think is central? carbon, and you're of course going to use brackets with a negative charge, right?
Yes.
So we've got C. Now what do you want to do?
Two single bonds.
Hang on, we're going to go O, O, O. Where's the H going?
Well,
One of the others.
but not because you have to put a double bond.
Hang on. All right, now what do you want to do?
Attach the O's to the C with two double bonds and one. I mean, two single bonds and
One
one
double bond.
Where's the double going?
The one on the
The
bottom.
one on the right.
Either one is fine.
Just not the one with the H, right?
All right, complete the octet.
And then you have to fill in.
All right,
But there's multiple ways that you could draw it.
You can move the H,
There's
don't move the H.
two
or
other
you
ways.
move the double bond to
Yeah,
the,
you just
the bottom.
So you want to flip these around?
Yeah.
But how do you know when you're supposed to make two and when you're supposed to make one?
Well, is it really a double and a single?
Technically it's 1.5.
Exactly. So you have resonance here. Now understand what this is saying. Two of the bonds are the same length because you don't really have a double and a single here. You really have 1.5. That's why these are the same length. Keep in mind, double bonds are shorter and stronger than single. Triple bonds are shorter and stronger than doubles.
Oh, so those short.
So
one
that's
long
why
one.
these were a little shorter than this. This is truly a single bond. And the way you guys did great with it, you're either brighter than they are, or we're in the resonance conversation, and so you put the two together, or it's not game day and you're not a nervous wreck, or you don't have to remember 57 concepts at one time and your head's going to explode, or it's not the first AP exam you've ever taken. So when you think about all of these factors, not to mention the lack of sleep,
Oh, yeah,
it becomes challenging. So you guys did great with it, but if we went back and looked at all the booklets from my students, it was a bomb.
Well, what happened if you only drew one of those structures?
Would it be wrong? Because it said diagram
Because it
or
said, yeah, it said diagram or diagrams.
You probably have partial credit.
Well, it said or, so it doesn't always mean you have to.
What we are seeing more and more of is that they are dropping so many hints for you, making it a little bit easier. Let's look at the point value that was assigned. Here are your resonance. 1 point is earned for a correct Lewis structure. 1 point is earned for indicating resonance.
You have to do two
So you have to put the arrows?
for resonance.
Well, you
Yeah,
can put
resonance.
it like I did it.
Yeah, yeah.
So should
Yeah.
we always, anytime there's multiple bonds, we should always look for resonance?
No, it's not that common, but they dropped so many hints that you knew it was here.
By saying
When they
that
say
it was-
like A's or R.
That's one possibility, although you could have just had an isomer, but the bond length really was the key.
Okay. So if they talk about like bond lengths in any question, we should always try to find resonance. Okay.
Not always. It's not super common.
I'm just
Sounds
gonna
okay.
Yep.
So mean.
Okay, so carbonate ion has 2 minus charge, right?
Yes.
And then when you add that, are you adding proton? Is that why it becomes?
Yes.
So what about, how does a dihydrogen carbonate ion still have a charge?
It doesn't. If you had hydrogen carbonate H2CO3, that's not an ion anymore.
Okay.
All right, but that's a good point. And the last point I want to raise here. Keep in mind with your oxyacids, So you have a bicarbonate ion. If you had the oxy acid, hydrogen carbonate, H2CO3, where would the next H go?
On the C.
No.
On the other
It still goes on the O, and that will be important when we get to acid bases.
Because you can't connect an O to an O, so you have to.
You usually don't, except in peroxides and ozone.
Because then if you connected the H to the C, then you have to connect two O's together. 'cause
Well, especially you can't just plop it right on there because you're going to make the dreaded 5 bonds on carbon, which is an absolute no-no. All right, at this point, you should have some comfort level with drying compounds, drying polyatomic ions, starting to introduce resonance. After the break, we're going to draw compounds that have incomplete octets, odd number of electrons, and expanded octets. This is taking it to the next level. You have a foundation. You should be very comfortable with it, and we'll get a little practice in as well. And we'll do that in the